Hey guys, Mr. Backerberg here. In this video we're going to look at orders of magnitude and logarithmic models. Now sometimes as we're comparing values, their size can span a pretty big range, and that's why scientific notation was developed. So let's talk about some things out in space, and let's first talk about Mercury. Mercury is about 57.9 billion meters away from the Sun. But if we compare that to Pluto, Pluto is 5,900 billion meters away from the Sun. So it's about 100 times further away from the Sun than Mercury is. Now if we think about those things in terms of scientific notation, Mercury's distance we can think about being 5.79 times 10 to the 10th meters, compared to Pluto, which would be 5.9 times 10 to the 12th meters. So now as we're looking at those exponents in our scientific notation with a 10 power and with a 12 power, we can see that there's a difference of 2 in those powers. And 10 being raised to the second power is a difference of 100, meaning that Pluto is 100 times further away from the Sun than Mercury is. Now we can also compare these distances by finding their order of magnitude. And in order to find the order of magnitude, we're going to use a common logarithm, or a base 10 logarithm. So what I'm going to do is take the log of each one of these scientific notation numbers. Now if I do the log of 5.79 times 10 to the 10th power, I'm going to get about 10.76 as my answer. And if I do the log of 5.9 times 10 to the 12th power, I'm going to get about 12.77 as my answer. Now as I'm looking at these order of magnitudes, I can see that there's a difference of about 2. So we could say that Pluto's distance away from the Sun is 2 orders of magnitude greater than Mercury's. And again, this order of magnitude is kind of referring back to those powers. We saw that there was a difference of 2 within the powers in that scientific notation, which meant that Pluto was 100 times further away than Mercury. Same thing happening with the order of magnitude. Because there's a difference of 2, if we think about 10 being raised to the second power, that really means there's a 100 times difference. Now, one way we see orders of magnitude getting used is to compare earthquake intensity. And earthquakes are measured using the Richter scale. And to calculate a Richter scale value, what we do is we take R equals log of A. And A stands for the amplitude of the vertical ground motion at the receiving station. And they measure that in micrometers. And this A is going to be over a T value, which is the period of the associated seismic wave in seconds. And then on the end of that, we add on a B value, which accounts for the weakening of the seismic wave as we increase distance from the center of the earthquake. Now what we're going to do is compare a couple of earthquakes. So let's say we have an earthquake that measures in at 7.9 on the Richter scale, and we want to compare that to an earthquake that measures in at 5.9 on the Richter scale. So if we think about what's happening in here with our Richter scale formula, if we were looking at computing this R1 value of 7.9, we would take the log of our amplitude. Now we don't necessarily know the amplitude, so I'm just going to call it A1 over T plus B, and that would equal our 7.9 value. Now if we were calculating the second Richter scale value of 5.9, we would take the log of some different amplitude. So I'm going to call that one A2 over T plus B, and that's going to equal our 5.9 value on the Richter scale. Now if I were to find the difference between these, so if I were to subtract these, what's going to end up happening in here, I'm actually going to work this subtraction right to left because it's going to be easier that way. If I take the 7.9 minus 5.9, that's just going to be 2. And if I take B minus B, those are going to cancel each other out. Now with these two logarithms in here that we've got, we don't have any actual numbers in there right now, so there's not any actual simplifying that we can do. So I'm just going to write this as the log of A1 over T minus the log of A2 over T. But when we're dealing with logarithms and we have subtraction, we can condense those down using our quotient property. So I can actually write this as the log of A1 over T over A2 over T. But now what's going to happen in here with these fractions? When you're dividing by a fraction, it can be simplified by multiplying by the reciprocal. So really, I'm going to take a1 over t and multiply it by t over a2. So then those t's would cancel each other out. So then my fraction is just going to say a1 over a2. So I can write this as the log of a1 over a2 equals 2. And then if I write this in exponential form, so this would be 10 squared equals a1 over a2. And when we're dealing with that 10 squared, well, we know 10 squared is 100. So as we're looking at what's happening in here with these Richter scale values, a Richter scale difference of 2 really corresponds to an amplitude ratio of 2 powers of 10. And we know that 10 squared is 100. So we could say that that first earthquake, which clocked in at 7.9 on the Richter scale, is 100 times stronger than that second earthquake that registered at 5.9 on the Richter scale. Now, another way that orders of magnitude get used is when you're comparing acidity of chemical solutions. So in chemistry, the acidity of a water-based solution is measured by the concentration of the hydrogen ions in the solution, and you measure those in moles per liter. When you're writing out the hydrogen ion concentration, you write it as H+. Now, a lot of times these concentrations involve negative powers of 10, so we're going to use negative orders of magnitude to compare the acidity levels. Now, to measure something's acidity using pH, what we do is we take the negative logarithm of the concentration of those hydrogen ions. More acidic solutions have a higher hydrogen ion concentration and a lower pH value. Now, let's say we wanted to compare some things, and let's say we had some vinegar, and that vinegar had a pH of about 2.4. And let's say we also had some baking soda, and our baking soda has a pH of 8.4. Now, the first thing I want to look at finding is the hydrogen ion concentration for each one of these solutions. So to calculate pH, we said that we were going to use negative log of that hydrogen ion concentration. So for this vinegar, this would equal 2.4. Now, the first thing I'm going to do is get rid of that negative that's out in front of my logarithm by dividing the negative over to the other side. So this would be the log of my hydrogen ion concentration is equal to negative 2.4. Now, this is a base 10 logarithm, so if I want to write this in exponential form, this would be 10 to the negative 2.4 power equals that hydrogen ion concentration. And if we take 10 to the negative 2.4 power, in scientific notation, we get about 3.98 times 10 to the negative third, and that would be moles per liter. Now, if we were looking at this baking soda instead, I would approach it the same way. So the first thing I would do is divide that negative over to the other side. So we've got the log of our hydrogen ion concentration equaling negative 8.4. And again, this is a base 10 logarithm, so I can rewrite this in exponential form by going 10 to the negative 8.4 power equals my hydrogen ion concentration. And if I take 10 to the negative 8.4 power, I get about 3.98 times 10 to the negative ninth. And that's going to be moles per liter for our hydrogen ion concentration again. Now, as we're looking at this scientific notation, we can see that there's a difference of 6, meaning that there's a 6 order of magnitude difference between these two solutions. And same thing as I look at the pHs, we can see that there's a difference of 6 in the pHs. Now, 6 orders of magnitude really means 10 to the 6th power, which is 1 million. So the hydrogen ion concentration of the vinegar is 1 million times higher than that of the baking soda. That's going to be it for this video. Thanks for watching.